Okay, so we were talking about how to compute the force acting between the rollers and the work part. And then we said that we should multiply, for an approximation of this force, we can multiply the average flow stress by the contact area between the rollers and the work part. And the contact area is equal to the contact length times the width of the part. Okay, so in general, for L, we have an approximation formula, which is radical of the radius of the rollers times the variation of thickness here between T0 and TF. So T0 minus TF. Okay, in this way we can calculate. Yes.
بس ما فهمت شو الرسمة اللي رسمتيها عن ال contact
Okay.
length.
Okay. Look, your work part مش عندها a certain width W.
اوكي هيدي ب 3 دي. اوكي فهمت.
هيدي بال 3 دي. So إذا برسمها هيك, let's say like this, I do the same profile and a certain width. يعني the area of contact, okay, like it's like this. So the area of contact حتكون the contact length, okay, times the width. Okay?
Yes, okay, thank you.
Well. Now, where Y represents the average flow stress and the product WL is the roll work contact area. The contact length can be approximated by radical R times T0 minus TF. Now, once we calculate this force F, we can determine what is the torque needed to operate the rolls. Okay, so the torque in rolling can be estimated by assuming that the roll force is centered on the work as it passes between the rolls, and that it acts with a moment arm of 1/2 of the contact length. So to understand this, if you go back to the figure, if I go back to the figure, I can approximate the force as a resultant passing by the center of the arc of circle, okay? And since theta is small, I can approximate the arc of circle by a segment. And here I can consider that this segment here, this segment is of length L over 2. So this is L over 2, okay? So if I want to find the moment the torque required to perform this operation, okay, about the moment about the torque about this point will be equal to the force times L over 2. And since I have two rollers, the total torque that should be developed will be 2 times F times L over 2. So the total torque for the two rolls will be F times L. Okay. So going back to the formulas, as we said, for one roll, the torque required is 0.5 F times L, and the power required to drive each roll will be the product of the torque and angular velocity. So if we know the number of revolution, if you want per unit time, then the angular velocity is 2 pi times n, where n represents the rotational speed of the rollers in revolution per minute or revolution per second. Then from the number of revolution per minute, so n in general has a unit of, for example, revolution per second. If you want to deduce the angular velocity, you know that the angular velocity is in radian per second. So you should multiply, you know that each revolution corresponds to 2 pi radian. So it's times 2 pi. When you multiply by 2 pi, then you will get the angular velocity omega, for which the unit is radian per second. Okay, so, and we know that the power, what is the unit of power? Power is in watt. Okay, to calculate power, or you do force times linear velocity. Okay, or so it is or F times V, or it is torque times omega. Okay, so the torque unit is Newton meter, and the angular velocity unit is radian per second. and radiant is no unit, doesn't have unit. Okay, so when you multiply Newton meter by radian per second, you get unit joule per second, and joule per second is what? Is power. Okay, so if you want to calculate the power required to perform your rolling operation, you should say that for each roll I need to provide a torque of 0.5 FL. So for 2 torques, I need to FL as a torque. And by multiplying by omega, which is 2 pi n, you get that the total power is 2 times, because I have 2 rollers, so 2 times 0.5 FL is FL. And I multiply by the angular velocity, which is 2 pi n. I get in total that the total power needed to operate the 2 rollers is 2 pi n times FL, where the power is in watt or joule per second, n is the rotational speed. It can be in revolution per minute or in revolution per second. But in order to obtain at the end the power in joule per second, I should convert it to radian per second. Okay. And of course, F is the rolling force. If I am working in SI units, I take it in Newton. And for length, I take meter. If I'm working in English system of units, for power, it is inch lb per minute, for example. For rotational speed, it will be in revolution per minute. For F, it will be in lb. Okay, and for L, it will be in inch. Any question on this part? This is the part related to calculation of flat rolling. So you should, this is posted for you on Blackboard with problems. With the problem section, you have a part processes equations for chapters 14, 15, 16. Okay, so now we covered a part of it because the other part is for chapter 16. Okay, so you will stop until now, until here. If you can revise this document, because next time on Wednesday, we will do problems on this part together. Okay. Now I want to just show you the formula sheet. We have a formula sheet summarizing all of these formulas for chapter 14 and 15. It's also posted on Blackboard. So here you can see all formulas of chapter 14 and 15, which were covered. So you should know a true strain is L final over L0. Flow stress is given by YF equal to K epsilon N. Average flow stress is given by K epsilon N over 1 plus N. The strain rate is V over H, where V is the ram velocity and H is the instantaneous height. You have the strain rate sensitivity equation is C times epsilon to the power m. All of these equations, we found them in the problems we did today. Now, with the introduction of chapter 15, we have introduced what is draft. Draft is the final, it's T0 minus T final due to reduction in thickness during rolling operation. We have also the reduction factor, which can be defined as the ratio of D over T0. The maximum draft that is possible in rolling operation is related to the radius of the rolls and the friction coefficient between the two surfaces. We will see that in case we need to achieve a higher draft than D maximum, we need multiple passes. So the minimum number of passes will be equal to the total draft to achieve, which is T0 minus TF, over the maximum draft per pass. Okay, so this will give you the number of passes, the minimum number of passes required to perform the operation. Now, from conservation of mass, we can relate the input parameters to the output parameters. T0, W0, V0 equals to T final, W final, V final. Concerning the roller tangential speed VR, you know that the linear speed is omega times r, angular velocity times r. And omega, it's 2 pi n. So to get the tangential roller speed, you just have to multiply omega by r. And omega, it's 2 pi n. So VR, it's 2 pi r times n. The forward slip will give a relation between VF and VR. which is V final and the roller velocity. The contact length can be computed as a radical of R times the draft, T0 minus TR. Concerning the rolling force can be approximated by average stress times L times omega, and the torque per roller is half FL. So the total torque for the two is 2 times half FL, it's F times L. So please pay attention here. This is, if you should know that this is per roller. This is per roll, while here the power is computed for 2 roll. Okay, for 2 watts. So here, just when you multiply by 2, you get the total torque for the 2. And to get the total power, you multiply by the angular velocity. Here, why is it divided by 60? So please, you should understand the formulas to know why here it's over 60, because here N is provided in revolution per minute. So if you want to convert, in order to find joule, the power in joule at the end, you should multiply first by 2 pi to get it in radian. And you should divide by 60 because you want to convert from revolution per minute to radian per second. Okay? Any question on this?
Thank you, Doctor.
So on Wednesday, please cover this part. On Wednesday, we'll start problems on it, on this part of chapter 15. Okay? Yeah, let's see you on Wednesday. Bye bye.